All right, now time for part two. What we're going to do here is we are going to add a switch. All right, so last time I had a battery there, and we came along here and we had a resistor and a capacitor in series, a resistor and a capacitor, and they came down here to ground. All right. Now what I'm going to do is I'm going to put a switch I guess we need a resistor here, and that's just to make it a real battery. Always wanted to be a real battery. So the switch is going to be like this. It's something we can open and close. This battery is open, then the circuit is this one, right? You just go around here, and that's your circuit, right? And it's exactly what we talked about last time. Now what I want to do is I want to take that switch and close it, right? So if I close the switch here, what will happen? Well, now we've got two possible loops, right? We have the outer loop, the big pink one here. We've got this one here, and we have this guy there. Now that I think about it, I probably should do that a little bit differently. So, hold on. All right, howdy. Now it's part two for this lecture on resistors and capacitors. What I want to do is I want to add a switch and see what happens. All right, so how am I going to do this? So we have had a battery here that's connected to let's do it over here. It's connected to this resistor and this capacitor that are in series, like that. And let's say we have a switch here. So the switch can either go to this point. I want the switch the other way. I want to have this higher probably. So we'll have a switch here, and the switch can either go here or here. All right. And that switch, this one over here, just comes on straight down to the ground. Right, so that'll mean that if I put this switch in the gold position, like this, what will happen is we'll have the same setup we had before, delta V R C. This capacitor will charge up to its maximum charge, right, which was the capacitance times delta V, and that resistor wasn't important. Now, what we want to do is we want to switch from that gold situation to this silver situation here. I hope it looks different. The markers look different. All right, and oh, that's not silver, that's why. Okay, it's a green one. Maybe it's bronze. I don't know the names of these colors. So here's the silver one. All right, so we've got the silver one here. It just looks like the smudges on this side. I don't know what they look like on your side. All right, and then we have this little loop here. In this case, all we have is a capacitor times a resistor in that's connected to this ground, right? So there's no increase in the potential. The increase in the potential takes this thing. This whole thing is at delta V, but everything else, here to here to here to here, is at V equals 0. Except that this thing is charged like that. So according to that, the maximum Q, if everything's connected to here to 0, is going to be 0, right, in the steady state. But initially, it's not in the steady state. And it's not in the steady state because, well, for one thing, the charge on the capacitor is this previous charge, right? And so this has a higher potential than this. So it has the same potential that it originally had from the charging of the battery. Which means that now, if all this is at 0, and this has a higher potential than this, there's a potential across that resistor, at which point the current begins to flow out of the capacitor and into the ground, until the ground neutralizes the capacitor, discharges the capacitor is what we call it, right? We get rid of the charge, discharge. So that's basically what's going to happen here. We want to talk about the discharge in these capacitors. So a resistor, which could be just a wire if we wanted to, a real wire, not an ideal wire, that shunts a capacitor that shunts. Shunt is a good word. To ground. It's not. We could do something more complicated. I don't think we will. We'll discharge it. Doesn't actually have to go to ground is what I was thinking about. You know, if we have this loop, right, it doesn't matter whether or not this is connected to the ground, because there's still going to be the same charge or the same potential here as here. So this is going to still discharge, but then we have a harder time figuring out what the potential is, right? So, you know, we'll just err on the side of caution and do it the easy way. And what's going to happen here is the charge will decay exponentially. The charge will decay exponentially. Okay, and so what does that mean? That means that if you were to draw this, somebody's got to be a little wet, right? Come on. If you were to draw this, you would have your charge on the capacitor versus time. Let's see how close am I? I'm pretty close to the edge, aren't I? And it'll just drop off like that. Basically, and this will be your initial charge, and it'll just drop off. Basically what that means is the more charge there is on this, the faster it discharges. All right, so if you have, let's say, 10,000 charges on here, then it'll take just as much time to reach 1,000 charges as it will from 1,000 charges to 100 charges. Okay, that's more or less what the exponential decay means, is that how much you have of something determines the rate of change of the thing. So basically you can think of this as, for every one of those charges, for every second, there's a chance that it will flow to zero. And that chance stays the same for every unit of time. So it's just like rolling a die, right? You roll a die and you say, okay, if I get a 1, that charge is going to flow to 0, right? If I get a 2, it's going to stay there. If I get a 3, it's going to stay there. But every time I get a 1, it flows to 0, and I reduce the capacitor here. And for every second or whatever it is, I roll that die for every one of the charges on that capacitor. All right. So that means the current charge is going to be the initial charge times, oops, it's supposed to be backwards, not upside down, e to the minus t over RC, the product of R times C. So that's a really nice result, and it would be nice if it was something we could explain here without calculus. But basically R times C is the amount of time it takes for the amount of charge on the capacitor to become 1 over E times that charge. So I should have thought that out. It's still more than a third, but less than a half, maybe 40% or so. So, I mean, you have to figure that out. If you want to figure out exactly what it is, use your calculator, 1 over E times 100. Okay, so this describes this line. And B, the same happens for the current. So you remember, with Ohm's law, the current is proportional to the voltage. And from our capacitor relationship, the charge is also proportional to the voltage. So that means as our charge decreases, so does our current in different units, right? This is our amperes, this is in coulombs, but for the same reason, because the rate of current change is proportional to the initial current, or the current, you get the same idea. So I think this is Q over RC times e to the minus t over RC. And I guess it's got to be Q0. And at least I agree with myself that that's not always true. So in this case, we have the same sort of thing happening while this is discharging. As this is highly charged, it discharges quickly, which means you have a high current. When this charge gets lower, it has a smaller voltage difference over the resistor, so it has a lower current, which means it's slower to discharge. So the discharging starts fast and goes slow, all right, until you get to a point where it doesn't matter anymore. Usually that's e to the minus 5. So that would be 5 RC as the time. All right. So that's the basic idea behind discharging the capacitor. Sometimes you want to discharge a capacitor because, I mean, that's what you can do in a DC circuit with a capacitor is store charge, store potential for later use. You can do that for all sorts of reasons. You can do it to stabilize the current. You can do it to provide a little bit of something after you turn off a switch, for example, so that you can still power a power down sequence, for example. So, although that might be a lot of charge. So you can use this technologically to do things for you. And that's something good. All right, so next, what we'll look at is, what should we look at? We'll look at charging the capacitor. All right, I'll do one example for this, and then I'll probably do a more complicated example when we do the charging of the capacitor. All right, bye now.